So, well, thank you so much for the introduction, and thanks everybody for coming here today. I have family from different parts of the country here today as well, and parts of California, and also Avery's family who traveled all the way here. And so thank you for coming. It means a lot to me. So I'm going to share my PhD research that has really taken over my life for the past 4 years or so on the molecular composition and chemical aging of organic aerosol from various types of smoke. And I'll try to go between both monitors, but I tend to favor this side. Maybe not. All right. Okay, so I'm going to start off with a little bit of background about atmospheric aerosols. So if you were at Avery's talk earlier today, you would have heard a little bit about this. But I want to define what is an aerosol. So an aerosol is composed of liquid or solid droplets or particles suspended in gas. And so when most people think of aerosol, they think of hairspray. I happened to use hairspray this morning, and I was reminded of the definition. That was the first thing I was going to talk about. But in terms of the atmosphere, we classify them in different ways. So the first way is primary aerosol sources. And these are emitted directly into the atmosphere. And so some examples of this are sea spray aerosols. So for the surfers in the room, you have waves crashing on the shore, you get sea spray aerosol. In addition, biomass burning. So wildfire events produce a lot of organic aerosol into the atmosphere, and that's going to be the main component of my talk today. You can also have volcanic eruptions or dust storms that also emit aerosols directly into the atmosphere. In addition to that, you can have secondary organic aerosol, and that's formed by reactions of gases with atmospheric oxidants. And so this is a separate process where I'm showing here isoprene and alpha-pinene, which are common volatile organic compounds that are emitted from trees or biogenic species. And they can undergo atmospheric oxidation by the OH radical that's pretty ubiquitous, or ozone in more polluted regions, or the nitrate radical during nighttime that's primarily important. And then they can form semi-volatile organic compounds, and these compounds have different chemical properties and composition that can then undergo different reactions or processes in the atmosphere, like evaporation and condensation reactions to form secondary organic aerosol particles. And so what does this mean on a global scale? Well, the atmosphere is not stagnant. We know that it moves. We know that different types of aerosols are emitted and it can mix together. So in this NASA GEOS-5 simulation here, I'm showing 4 different aerosol types. So in red is dust aerosol, in green is organic and black carbon. And so the combination of these two together will be important for my talk today. White is sulfates and blue is sea salt. So as you can see, it's a pretty dynamic system, the Earth, as you know, and green and red aerosol does mix together. So what happens as aerosols transport around the globe is that they can chemically age. And so in my talk today, I want to talk more specifically about some processes that go on. And so why do we care about this? We care about this for 3 broad reasons. The first of which, and this is not in any particular order of importance, but air quality and visibility. So in this example here of the Chrysler Building in New York City, I'm showing what the visibility looked like before and after the Canadian wildfire plume came into the city last year. So visibility was very poor. In this New York Times article clipping, you can see people were wearing masks outside again. So this is 2023 summer. But the wildfire brought so much particulate matter into the city. It was pretty unhealthy air quality for people to breathe in. They didn't feel safe. They started wearing masks outside again. And so in terms of human health, we know that particulate matter smaller than 2.5 microns can lead to cardiovascular diseases, asthma, other respiratory illnesses, and cancers if they're inhaled and deposited within the lung tissue. And then in addition, for climate, we care about aerosols for a few different reasons. We know that certain greenhouse gases have a net positive radiative forcing effect or a warming effect on climate. And sometimes carbon dioxide as a greenhouse gas gets a bad reputation, but I want to point out that if we didn't have any CO2 in our atmosphere, it would be way too cold for life. There would be no water that was liquid. It would all be frozen. The average surface temperature would be about 0 degrees Fahrenheit. In addition to that, there wouldn't be any photosynthesis, there wouldn't be any trees, you get the point. And so for aerosols, if you look in this middle section here, what you'll notice is that for aerosols, they're split up into different colors, and they straddle this middle line here. So we know that for black carbon, these are things like soot, they actually have a net warming effect. But for colored aerosol, or colored organic carbon, like brown carbon, there's much more uncertainty there. So it can either cool or it can warm. So in my PhD, we were looking to see what effect does aging have on that metric. All right. So I talked about organic carbon. I'm going to talk about it a little bit more. So there's 3 different optical classifications here. You have organic carbon that's colorless. These are lower molecular weight species, hydrocarbons and their derivatives. I'm not really going to focus on that today. I'm more interested in colored things. So black carbon is the other extreme here. Oops, wrong way. And black carbon, sometimes called soot or elemental carbon, is composed of these graphene layers stacked upon each other, and it has really high absorptive properties. And on the other hand, in the middle there is colored organic carbon. So this is where the majority of my talk is going to be focused today. This is on brown carbon. And so polycyclic aromatics make up brown carbon, like benzoyl pyrene is an example I'm showing here. Other biopolymers and humic-like substances as well. And so how do we compare the absorptive properties between brown and black carbon? I'm showing this example from my collaborator Alex Laskin's group. They had a review paper in 2015 where they looked at defining brown carbon and black carbon and what it means in the atmosphere. And this black line here, the solid one, is just black carbon. And so what you're seeing there is it has a power law dependence of 1. The light attenuation, so that's on the y-axis here, of black carbon is pretty low across the wavelength ranges of interest here. So this is the UV, the visible, and the IR. But then for these VBOA samples with the blue circles and the red triangles, what you notice is that power law dependence is much higher, and that's because it's a mixture of both brown and black carbon. So if I look in the literature and show you an example, or 6 examples, of the percent of light absorption as a function of wavelength contributed by brown carbon or black carbon, what you'll notice in each of these examples is that as you increase your wavelength of interest, the percent of light absorption contribution by black carbon increases, and on the contrary, brown carbon is decreasing as you decrease your wavelength. Right. And so chemical aging of VBOA, you have a fire, you have primary emissions that can level off. What kind of chemical aging mechanisms can go on? Well, there can be multi-phase processing, there can be gas particle partitioning, there can be condensed phase chemistry going on, there can be oxidation reactions in the atmosphere by OH or ozone or M3. There can also be photochemistry going on. So if you're at Avery's talk, you learn all about photochemistry and the quantum mechanics behind that, which I'm not an expert in, so I'm going to stay away from that. But in terms of photochemistry, multi-phase processing, oxidation reactions, these things go on simultaneously in the atmosphere. And you can form aged brown carbon that has different chemical and optical properties. And so you'll notice in my little schematic here that some might stay the same color, some might darken, or some might even lighten. All right, and so that takes me to my dissertation goals. There are 2 folds. There's 2 parts of this talk with 4 papers that I'm going to try to get through. So I'll start on top, and that is just VBOA, or biomass burning organic aerosol, iron-3 condensed phase chemistry. And so we had 3 main questions that we wanted to address. We're looking at how do certain substituents of VBOA interact with iron? Can real VBOA that I produce in the lab undergo similar reactions with iron in order to produce secondary brown carbon products? And then how does this iron catalyzed chemistry impact smoke evolution as it transports around the globe? All right, and so for this, I'm going to highlight 2 papers of mine that Sergey already introduced a little bit of. But the first one was from 2021. And so this was a project that I jumped right into when I started graduate school. Actually did all the analysis from my parents' house in Los Angeles when I moved back there during COVID. And then the second project we published last year in 2023. And both of these works were in collaboration with Professor Hindela Badley's group in Canada at Wilfrid Laurier University. And the second work was in collaboration with Joe Patterson's group here at UCI and Dr. Brooke Carpenter as well. All right, so before I talk about those papers, I want to give a little background about iron in the atmosphere. So if I look at this review paper by Professor Hindela Badley in 2021, what you'll notice is that natural mineral dust is primarily found in the northern region of Africa and the Saharan region, along with Central Asia. And what this plot is showing is the primary regions in which mineral dust becomes aloft, and it's mostly coming from the regions I described. And so in this NASA Earth Observatory image from Saharan dust plume in 2018, you'll see that this dust gets picked up off the coast of Africa and can travel across the Atlantic Ocean where there's a lot of water and condensed phase chemistry going on. It can end up in the Gulf of Mexico, the United States, and even other parts of South America. And so if we want to know what the importance of that is, we need to know what type of minerals make up mineral dust. And so I'm not a geologist like Josh is. And so I read this paper where they categorized all the different minerals within mineral dust, and they found the relative abundance as a function of particle diameter. And what we know is that iron makes up about 3% of mineral dust composition, give or take. And then we also know that hematite is rich in ferric oxide. And so what I liked about this plot is you can clearly see that as you decrease in particle diameter, you're actually increasing the relative abundance of hematite that's present. And so what happens when iron oxides or ferric oxide is aloft? Well, it can dissolve. And so if I have a 20 micrometer cloud droplet, it's estimated that about 1 micromolar worth of iron 3 is there. This droplet can undergo evaporation down to about 1 micrometer in diameter, and it can range up to 1 to 10 millimolar in iron 3 concentration there. So I'm going to keep that number in the back of our mind as we move forward. I'm going to shift gears a little bit and talk about stages of combustion. And so in order for combustion to happen, you need to have, obviously, a biomass material, you need to have some heat, and then there's 4 different stages of combustion that occur. The first of which is distillation, so this lower temperature, and you're getting emissions of water vapor and terpenes here. It's essentially like dehydrating the fuel. And then after that, you can oscillate between these 3, depending on the environmental conditions. And so if you are under anoxic conditions, meaning there's limited oxygen there, you're going to undergo pyrolysis. And so this is typically between 300 and 800 degrees Celsius. And it's the region in which I focus my PhD on because it produces brown carbon in the most abundant way, with the greatest emissions of VOCs. And also the composition of emissions are temperature dependent. So as we increase our temperature, we actually can predict what type of products are emitted. Okay, so for biomass burning, there are 3 main biopolymers present in biofuels, if you will. So there's lignin, cellulose, and hemicellulose. Lignin is a complex cross-linking chain of phenolic precursors, whereas cellulose is a deep glucose matrix, and hemicellulose is a branched polysaccharide with 5 different sugar groups intermixed. And what you'll see here is as a function of combustion, you're going to get emissions of different things. You can have emissions of phenols, like catechol, aldehyde, glycol, and syringols, I'm showing here. You can also have some biomass burning tracer species, like levoglucosan and 4-nitrocatechol that Avery talked about earlier today. But you can also have polycyclic aromatic hydrocarbons at higher temperatures. This is more common under flaming combustion, but it does also happen under pyrolysis as you really push that temperature regime. And so what we wanted to know was, how does BBO8 evolve during atmospheric transport when it's exposed to atmospheric iron? And so to do this, you do what every graduate student does. You go look in the literature. Has this been done before? And if so, does survey know them? Can we talk to them? So in 2015, this paper out of Hin's group, they looked at hematite and the reaction with catechol and glycol. So what they did was they took hematite, they dissolved it, they made a slurry at pH 1, they let it age for 10 days, they took the filtrate off, and they adjusted the pH back to 3. Then they added catechol in this upward arrow and then glycol on the bottom. And what you saw is this stark color change. And so the top catechol reaction turned black. They're able to filter out particles from it that were not there before. And then for glycol, there was this burnt orange color where they filtered out particles as well. And so they went and tried to see what these particles looked like under the microscope, and could they find what the chemical composition was. And what they found is that there was no iron in these particles. So the iron stayed in solution, but the particles, the precipitate that was formed, was completely organic. And so that was very interesting to me. When I was starting my PhD, I wanted to know more. And so I was able to collaborate with Henry Chin, who's a former undergraduate from Sergey's group, and Dr. Warren Fleming. And what we did was we conducted experiments, but this time we expanded the list of things that are present in BBOA, but can also react with iron potentially. And so we chose catechol again as our control. Then we used 2,4-nitrophenol, 4-nitrocatechol, coniferaldehyde, 3 and 4-hydroxycatechol, and methyl catechol. 4-methyl catechol. And we reacted them in a similar fashion with iron chloride, in 2-to-1 iron organic ratio. And what you'll notice in this picture is that the organics are pretty much clear. But then once you add iron, the solution changes to green. And within an hour, it's completely black. And then we filtered the particles out for the reactions that produced them on this 2-hour time scale. And they were very, very dark in color. And so that was interesting. And so we monitored using UV spectroscopy. I'm not going to get into every single trace that's on this plot, because there's a lot of them. But we monitored the reaction before we added iron. I guess we took an absorption measurement of just the organics that were there, and then we added iron to it. And so I want to talk about just catechol first here. And so in this measurement, we have in red the organics trace. So there's really no absorbance greater than 300 nanometers. There's a peak at 270 nanometers. And once we add iron, we notice something interesting in the yellow. So this yellow trace here, we have a ligand to metal charge transfer band in the near IR. And mechanistically, what this means is iron 3 has complex to this catechol molecule, and iron 3 was then reduced to iron 2. And by doing so, we have this spectral feature occur. And then after that, or I guess simultaneously, we have this intermediate that was formed at 400 nanometers. I say it's intermediate because it forms and then goes away. We don't see it again. We believe that it's a 1,2-benzoquinone structure. Depending on the other substituents for the other reactions, some type of 1,2-benzoquinone derivative, if you will. And then after that, we started to observe just mass scattering effects, and that's indicative of essentially a baseline shift. So you're increasing absorption across all wavelengths here. We believe that after iron 2 was released from this complex, it's reoxidized back to iron 3 through reaction of hydrogen peroxide to produce OH in solution. That OH reacts with your intermediate, and then we form polycatechol in this case, or oligomers. And so for 3 and 4 hydroxycatechol and conifer aldehyde, we wanted to know what were these particles made of. And so we extracted them with methanol and we ran them on the analytical trifecta, is what Avery called it in his talk, but it's the Orbitrap high-resolution mass spectrometer instrument. So how this works, it's composed of an ultra-high performance liquid chromatography column, that's number 1 here, coupled to a photodiode array detector in 2. And then a high-resolution mass spectrometer in 3 and 4. And in 3, I'm showing an electrospray ionization probe that we use in my work. And so what we do is we can insert or inject our sample into this column, and we can take an in situ absorbance measurement and couple that to a mass spectrum at each time point. And so we have a good idea of what's absorbing and what is the potential chemical composition of it. So if I was looking for chromophores, like I was in this part of my work, what I observed for the 3-hydroxycatechol reaction was a tetramer, meaning the main light absorbing species there were 4 of these complexes together, 4 molecules together. And then for 4-hydroxycatechol, we saw dimers, and for conifer aldehyde, we saw dimers and trimers. And I will note that for 4-hydroxycatechol, we saw trimers and tetramers as well, but they weren't the main piece in that reaction. And so in summary, what did we learn? We learned 3 different things. The first thing we learned is that compounds that had adjacent hydroxyl groups on the ring produced particles. So in the case of 2,4-dinitrophenol, this did not produce particles and it didn't complex with iron. And then secondly, you might say, well, Katie, there's 2 OH groups here on 4-nitrocatechol. How come that didn't produce particles? Well, this group, the NO2 group in the 4 position, was 2 electron withdrawing. We did see a complex form with iron, but it couldn't go past this step. So we didn't see any particles form in that reaction. And then you might say, well, Katie, there's another species here that form particles that does not have an OH group in the 2 position. You're right, it's a methoxy group in the 2 position. But if you ignore this tail in the 4 position, you actually end up with glycol, which I told you earlier does react with iron to produce particles. So we believe it reacts with iron in a similar mechanism to glycol. However, this tail, this substituent in the 4 position, is too big and it sterically hindered more of these species from combining together. All right, and so then we wanted to take this a step further. And so naturally, what we did was we started burning stuff. So we had some Canary Island pine needles in our lab that Natalie Smith, who's here today on Zoom, she was using in her experiments for, she was actually keeping the tree alive and using it to make SOA in our chamber. And so I took advantage of all the needles she left on the floor and I started burning them. during COVID time. And so what I did was I put them inside of our tube furnace under their flow of nitrogen. I pyrolyzed them and I collected the particles on a Teflon filter here. So that's what I'm showing in this picture. These are actual photographs of my filters between 300 and 800 degrees. And so our goal was to see how iron can react with this complex mixture that's produced in a more realistic fire scenario. All right, and so the reactions were essentially done the same way. We added, well, first we extracted each filter in water. So we had a water-soluble extract. We had iron chloride in a 2-to-1 molar ratio. We let it react. We monitored, we did the spectroscopy. We ran high-resolution mass spec again. And then we looked at the particles that were formed. So I guess that's a little bit of a spoiler, but we used electron microscopy and energy dispersive X-ray spectroscopy for that. Okay, so now I'm going to break up my talk a little bit into lower temperature versus higher temperature, and that'll be apparent in a minute or two. But for lower temperature, that's 300 and 400 degrees. What I'm showing here are going to be the absorption measurements. On the left, this is the full wavelength range between about 230 and 700 nanometers. And then on the right, I zoomed into this box region visible range. We've observed similar things as before. So with catechol, well, not catechol, with this water-soluble organics, this is just the OA in water, so there's no iron in that. And what you see is there's an organic band peaking at about 290 nanometers, and that goes away once I've added iron, and we notice this iron oxide band at 286 nanometers, and then we see an intermediate forming in the visible. So this is at 477 nanometers instead of 400, like in the pure catechol case, but we expected to see something different there because it's, you know, a mixture. And so over time, that intermediate peak goes away. We start to see some scattering in the solution. And so we ran high-resolution mass spec on this. What we found is that there were certain phenols that were present before I added iron, and that made sense. And so then I analyzed the particles in the exact same way, and I found dimers and trimers of catechol and conifer aldehyde again. So it was really exciting that we were able to see that there were products forming similar to our standard control experiments, but in this complex mixture. But to be honest, I was a little disappointed because I didn't see any cool colors, and we kept doing the same thing over and over again. It just really wasn't that exciting. And so I decided to just increase the temperature and try again. So I'm going to show you a slow motion video on the next slide. But what I did was I burned at 600 degrees and I repeated the same experiment. And so in this video here, you'll see me pipetting some iron chloride into this vial. And we're changing color from clear to this greenish brown color. This is a slow motion video, so it happened really, really quickly. But this green color was apparent to us. And then I let this reaction go on. And after about 30 minutes, I took a picture of the higher temperature reactions with iron chloride added, and they were very dark. And so it reminded me a lot of the catechol experiment on a slower time scale, but it was still going on. And then I wanted to go home for the day, like any good PhD student does. And so I went home and I came back the next day and I opened my drawer and my vials had these black particles settling out on the bottom. And I went and talked to Lisa and I was so excited about it. I remember I went to your office with my little vial and told Sergey, and he told me I was going to win a Nobel Prize. So it was so cool. And so we decided to remove the supernatant that was there and dry them in an oven for 24 hours. So they're completely black and dry. And these black particles were left on the bottom of my vial. And actually, this was a big mistake because the particles, once they were dried, I couldn't get them off the glass in any way. I couldn't extract them in organic solvents. I couldn't sonicate them. I couldn't destroy them with heat or strong acids or bases, caused a mess. We couldn't scrape them off the glass. We tried to do DART on them. That didn't work. We did MALDI and that did work, but I digress. And so it was clear to us that this particulate matter that was formed had a pyrolysis temperature dependence. And so we wanted to see why that was the case. So we looked at just the water-soluble extracts between 300 and 800 degrees. These are mass spectra that I took on the orbit trap of this material before I added iron to it. And what you'll notice is that over the course of increasing temperature, you start to lose some of these higher molecular weight species, and then catechol and glycol, some of these phenols actually start to dominate the mass spectra. And so this was interesting. And I looked in the literature and I'm like, why did this happen? And how come I only formed particles here, but I didn't here? And so I found this paper in 2018 where they talked about the 3 biopolymers and how they break down as a function of hydrolysis temperature. And I was like, yes, this is exactly what I need to know. And so lignin, cellulose, and hemicellulose break down as a function of temperature. After about 300 degrees, you have emissions of some phenols like soonjol. But then after 400, you start to be in this more phenol-dominated regime, glycol and phenol, and catechol, and some other things there as well. And so it was apparent to me that after 500 degrees, I was had way more phenols in my water-soluble extract that could react with iron in an efficient way. And so then we collaborated with Professor Joe Patterson's group, sorry about that, and Dr. Brooke Carpenter, and they're absolute experts in electron microscopy and all things materials. So I gave Brooke the solution of polycatechol as a control, and then I gave her my 600-degree reaction particles. And what they told us through transmission electron microscopy and scanning electron microscopy images is that the morphology of these particles were pretty much the same. The size, the agglomeration effects were also pretty much the same. These big stone-like things in these middle panels, it's just the substrate, so you can ignore that. But they're pretty much identical. So if I look at the energy dispersed X-ray spectroscopy spectra here, you'll see this big silicon peak. That's just a grid, so we can ignore it. But there's also big peaks of carbon and oxygen. So to us, that means that it's mostly an organic particle that's formed. There's also residual iron, but that's just from incomplete washing. And so we were able to call these particles polyphenolic since they were in a complex mixture. All right, and so now I'm going to shift gears and talk about the second part of my talk, which is on organic aerosol from the wild and urban interface. So this is like a house fire regime, if you will. So we wanted to know what is the overall chemical composition of smoke particles that are produced during urban fires. We wanted to know if we could identify any tracer species or ground carbon chromophores in this system, and how does exposure to UV or solar radiation in the atmosphere potentially impact the smoke absorption properties. All right, and so for this, I'm going to highlight 2 papers of mine, the first of which we published last year on photolytic aging of organic aerosol from hydrolyzed urban materials. And this was a really exciting project that we collaborated with Alex Laskin's group at Purdue. We were able to go to Purdue last year and talk about the paper and our results with him in person and see some of the instruments that results were featured in his paper with. And so that doesn't always happen. Sometimes you just send your samples to other institutions and they send you back the data. You never see the instrument in person, but that wasn't the case here. We actually got to work together and that was really exciting. And then in the second work here, this is in preparation still. We're planning to submit hopefully soon on the chemical composition and photolytic transformations of particle phase emissions at the wild and urban interface. Oh, and I forgot to mention that in the second paper, we collaborated with Jason Surratt's group at the University of North Carolina, Chapel Hill. It's math in here, so. I see. Okay. So first I wanted to find what is the wild and urban interface. So this is the region where human developments meet or intermix with undeveloped wildland. So this is very common in the United States, very, very common in California, where new housing developments are just built up until the foothills of mountains or up against nature preserves. And unfortunately, this is happening more and more where wildfires are jumping from forested regions and then going into urban communities and completely decimating them. And so why does this matter? Well, the smoke from these fires, first responders are the first ones there. They're going to be exposed to that. We want to know what's in it. Is it toxic? Probably is. And also, how does it evolve as it transports in the atmosphere? How does it undergo wet and dry deposition? What happens to surface waters if it has this ash deposited on it? What type of gas phase and aqueous chemistry can go on in the atmosphere with this type of smoke, and how does it affect people further downwind? And I looked in this National Academy of Sciences report from 2022, and they broke down by mass what the structure or contents of a home typically are. And what you'll see here is that the structure of a house is typically composed of woods, about 97%, which makes sense. And then about 2% is asphalt shingles, and another 2% of others, that could be like vinyl windows or glass, wood siding, PVC siding, other things like that. And then for contents, this is much more variable. So this is based off of personal preference. Some people have a lot of wood in their house. Some people have a lot of plastic. And other people have more or less fabric than others. And so we were looking to conduct a pilot study on this. It hadn't ever been done before. We wanted to burn a wide range of materials that are commonly found in urban structures. And so for this, I want to highlight a couple people. So Michael Alvarado was a really great post-baccalaureate student who worked with me for a little over a year, I think, or close to a year. He did a majority of these experiments that I'm going to show you today. And then Dr. Alexandra Clote, she helped us a lot with pyrolysis experiments, and she's a co-author on this paper, so I'm really thankful for her input. And then Alex Hoskin and Sharon G, who also contributed to this work. So we were looking for materials to pyrolyze. I asked Sergey about this. He talked to the building manager, Roland Hall, and the next thing I knew, there was a box on my desk with all these components of Roland Hall, like the ceiling tile that he brought in today. And so we pyrolyzed all of these materials separately in our tube furnace. Again, this time we only used 600 degrees. We were under inert flow of nitrogen again, of course. We collected the smoke particles on filters. And so Michael was really, really great at documenting everything. Never seen anybody be so organized with so many images. And he took pictures of every single filter. So all the filter pictures you're going to see are real, and they're from each experiment. So each of these pyrolysis runs, we were able to calculate the emission factors. That's the grams of collected organic aerosol in each filter divided by the kilogram of material we burned. And so we didn't pyrolyze kilograms worth of material. That's more relevant to a house fire. But in this case, our quartz tube that goes in the middle of our furnace is about an inch in diameter. So we were working more in the 200 milligram range. But as you can see, these numbers are different. We range from 1 up to, I guess, 47 for lumber. And so they had different emission properties. And then after that, we took each filter, we cut it into 4 pieces, and we conducted photolysis experiments. We left 1 quarter unaged, the other quarter half hour or 1 hour or 2 hour of photolysis time. And we placed it directly in the path of this xenon arc lamp with radiation between 280 and 400 nanometers. And so we put these long passive bandpass filters in here to filter out the light and keep it within its range. And then what I'm showing here is a picture that I took from the top of this setup where the filter is facing the beam. And so what I'm seeing now is the backside of the filter, but the material is actually on the front. And so we did photolysis directly on the filters themselves. And then after that, we dissolved each quarter in organic solvent. We took absorption measurements again. But what I'm showing here in this plot is the mass, the MAC value. So this is mass absorption coefficient. And I use this formula here in order to calculate that. And we use the absorbance value, but it's actually corrected for the mass concentration. And so if you remember the emission factors that I just talked about, they varied. The concentration of organics in solution also varied. And so using MAC values allowed us to compare among samples pretty easily. And so in the top, I'm showing a case for drywall, and in the bottom was thin PVC wire. And on the left is just the UV range, so that was between about 230 and 400 nanometers. And then on the right was the visible. And each of these insert plots are MAC values normalized to the unaged value. And so for UV, both drywall and thin PVC experienced the same thing. There was a decrease in MAC as a function of photolysis time. But then for the visible range, we saw something else. So we saw for drywall, there was actually an increase, and then for thin PVC wire, there was a decrease. And that was interesting because it corresponded to what we actually observed on the filters themselves. And so for the drywall case, the filter got way darker by eye. Michael showed it to me. I was like, are you sure this is the same filter? He was like, yes, it was. And so we extracted and took measurements. And then for the case of thin PVC wire, organic aerosol, we saw the opposite effect. So it was gray initially, and then after photolysis, it turned this light yellowish color. That was a photo-bleaching effect. So we redid this for all of the materials. And what we found was that 2 of them photo-bleached. That was carpet and thin PVC. The 2 remained unchanged, meaning there was no more than a 10% change in either direction of unaged to aged, the ratio of that. And then the majority of the species, 6 of the 10, photo-enhanced. And so if I then try to put this into context with other people's work in the literature, It's typically used optical absorption bins that I adapted here from this 2020 paper, where I'm showing very weakly to strongly absorbing brown carbon with black carbon as a reference here. And so how this works is you plot the absorption angstrom exponent against the log of the MAC value at 405 nanometers. And what the AE value is, if you will, it's how strongly the absorption coefficient is going to depend on wavelength. And so in the case of black carbon, if you remember from like a long time ago, I started talking about the power law dependence. The power law dependence here with black carbon is 1. So that corresponds to an AE value of 1, whereas brown carbon is much higher than that. And it's also much more variable. And so for all of the unaged fuels, I'm showing them in black here, typically fell within this very weakly absorbing brown carbon regime, but then after aging for 2 hours, we dropped down into this weakly absorbing brown carbon bin. So we had absorption enhancement overall with UV aging. All right, and so now I'm going to talk about the second paper that's in preparation. These are my high resolution mass spec results. And so we wanted to identify chromophores within these complex mixtures, and we had no idea what was in them. And so the way that you do this, you can use our Orbitrap platform again, and you can take measurements with your samples, but then you can also run standard compounds through them as well. And you can compare the PDA data, so the absorption spectra in situ of your sample versus that of a standard compound. You can compare that with the elemental composition that's determined by high resolution mass spec analysis using MSMS as well. And then you can compare retention time. So that's the powerful nature of using an LC instrument. Or GC in your case, Dawn. Don't want to leave that out. But I didn't do GC in this study. So for thin PVC wire, what I'm going to show you here in this top panel A is the PDA chromatogram in red, and then the TAC or total ion current chromatogram in black. So at 7.3 minutes, we have the most strongly absorbing time point in our chromatogram. And if I were to click in here and generate the mass spectrum at that time, that's what I'm showing here on the top right. And so there was this ion at 165 that corresponded to a C6H6 or C8H6O4 compound. And then I didn't know what this meant, and so I went and looked in the literature. What is PVC even made of? I came up with a list of things that maybe could have been that have this exact same molecular formula. And then I asked many people in the chemistry department, do you have these chemicals? Because we didn't have them. And luckily I got my hands on some of them, and I ran through our instrument, and I determined that phthalic acid, which is this molecule here, had the exact same retention time off of our column. The PDA absorption spectrum was the same, and then the mass spectra and the MSMS also looked identical. And so from that, we were able to identify phthalic acid as the main chromophore in this sample. And so this is where Jason Surratt's group comes in. They sent us very graciously a mixture of 100 different brown carbon chromophores that they compiled together, and they just published a paper on it. And we were really lucky to get our hands on this because as an analytical chemist, like Vero and Lisa, they were so excited when they heard I had these samples or these standards. You can run them through your instrument and essentially create a library. And so I had 100 different compounds that I was able to detect in my instrument. And then I had these unknown urban fire samples. And so I cross-referenced what I had in my standards versus what I had in the samples. And so I was able to identify 36 brown carbon chromophores, structurally identify them within my urban fire sample. That's never been done before. And so a couple things that stood out to me, I'm only showing a couple examples here, but phthalic acid and terephthalic acid are resins and plasticizers commonly used in urban material manufacturing, and I was able to identify them in my samples. All right, and so what does the chemical composition of this stuff even look like? So this is a plot I can show you where I calculated the double bond equivalent value, or DBE, which is just the number of double bonds or rings in the structure. And I applied that against the summation of the number of carbon and nitrogen atoms in my assigned molecule. And then in each of these shaded regions are predicted brown carbon chromophores. And so as you can see, there were a lot of species that were light absorbing in each of these samples. And so this is great. For carpet, about 42% of the species were predicted brown carbon chromophores. With aging, that number didn't really change. For vinyl flooring, we had a little bit of a decrease. And then for drywall, we had an increase. And you can see that there are certain diamonds here that grow or even shrink with aging. And that's fine, that's great, but it doesn't tell you really anything about what that particle is made of, what it means. So in order to understand that in terms of light absorption and potentially identify tracer species there, we looked at these three-dimensional photodiode array chromatograms. And so I'll take you through what that means. On the y-axis is the absorbance. On the x-axis is the time, so that's the time of our LC elution. And then on the z-axis is the wavelength. On the top is the unaged carpet, and then on the bottom is the aged carpet. And then the colors correspond to relative intensity. So if it's white, it has 0% absorbance, and then if it was black, 100%. We were able to identify benzoic acid and fumarate acid as two chromophores in our sample. But then after aging, you'll start to see that some of these peaks go away. So they were absorbing more at like 40%, and now they're down to about 20 or maybe even less than that. And so we believe that that corresponds with the photobleaching effects that we saw. And then if I contrast that to a case of photo enhancement, so I have fiberboard in the top panel and then aged in the bottom, you'll see that we have catechol and terephthalic acid, this chromophores we were able to structurally identify here. But then as a function of aging, this is a sample that photo enhanced or got visibly a lot darker with aging. And so there's just a greater absorbance across all wavelengths as a function of aging here. And so we thought that was really interesting. In comparison to what Avery was talking about earlier today, his chromatograms had like 2 peaks. Well, I have hundreds of peaks here, and it's not always easy to separate them. So we have to use tools in order to do that. All right. And so how does this compare with the literature? How does this compare with BBOA? Well, Dr. Lauren Fleming was an absolute expert in biomass burning, organic aerosol, and she published a paper where she used, I think, the exact same photolysis setup as me. And what she did was she took different biomass burning samples and she aged them under photolysis for 6 hours or 16 hours, and you can see the depletion of these chromophores over time. And so that's a much longer photolysis experiment than what I've already shown you with the 2-hour experiments, but on short time scales, so between 1 or 2 hours, typically biomass burning does increase in absorption, but then over time, if you let it continue to be exposed to UV light, it will photobleach or undergo oxidative whitening. So if you have ever put a black t-shirt out in the sun, just left it there for like weeks, you'll notice that it actually bleaches, and this is a similar concept to what I'm showing here. And so we did do some long-term experiments. Michael did them, so thank you so much for all the time, Michael, that you invested in these 18-hour photolysis experiments. And so I'm showing carpet in the top, vinyl flooring in the middle, and fiberboard, organic aerosol on the bottom, UV on the left, and then visible wavelength range on the right. And what we noticed was that after 2 hours, which is our initial measurement, carpet continued to photobleach. Whereas vinyl flooring stayed the same, and then fiberboard, we did experience that nature where we had an increase, but then it was followed by a decrease. But the end point here, the 18-hour mark, was actually still photo enhanced from the original unaged value. And so that's very different from common BBOA photolysis experiments. All right, and so now I'm just going to give a brief summary of my dissertation, with the exception of the baby work. It's not in this talk. But in part 1, I showed you that iron aging of biomass burning organic aerosol actually can increase the absorptivity of secondary products. So those were the black particles that were formed. And then in the case of urban fires, we had a varying effect on absorption with UV enhancement. So what does this mean in terms of the atmosphere? If I can summarize it in one sentence, it would be that smoke from both forest and urban fires can undergo different atmospheric processing in order to become darker in color. So another thing I'll highlight is that these particles that are formed are also much lower in volatility. So they can either be like deposited at the surface via wet dry deposition, or they can even be taking place as cloud condensation nuclei to have further effects on climate and precipitation effects. And so typically, when you have more darker aerosol, it's formed, it has implications for radiative forcing and things. All right, and so with that, I want to thank a lot of people. So there's quite a few names on here. My committee members, so of course, Sergey, my PI, my advisor, Professor Jim Smith, thank you so much, and Professor Manabu Shirawa. I want to thank all my collaborators, so Professor Hindal Badley, Brooke Carpenter, Joe Patterson, they worked with us on the Iron Project. In addition, Alex Oskin's group, Dr. Chang Chi, Professor Alexander Laskin, for all their help with the urban fires work. In addition, Jason Surratt's group, Dr. Bios Molchos for his input with the brown carbon standards. And there were two papers of mine that I didn't talk about at all today. So the vaping project was one of those. Dr. Robert Waltman, Megan Burkanian, and Professor Rufus Edwards, we worked together on the vaping project, in addition to the Blake group. Thank you so much for that. In addition, the Laskin group at Purdue, they were so kind to us when we went and visited Purdue last year. Dr. Kyle Siemens and Diego, they showed us everything about how to analyze ground carbon samples, what their orbit looked like, how to install the correct ventilation for APPI, because we weren't doing that right. And they taught us a lot of things, and they really took the time to do that, so we're very appreciative of that. I want to thank everyone in AirUCI. So this has been a really great place for me to do research. So specifically, I want to thank Dr. Lisa Wingen and Dr. Carol Perot, whose knowledge I wrote in my acknowledgements is just scattered throughout my dissertation. So all 330 pages or so of it is just sprinkled with all of your knowledge. And I think that goes for every other PhD that comes from AirUCI. So thank you so much. Adam Thomas, thank you so much for your work as an instrument overlord or operator. And so Lisa, Vero, Adam, and I were caretakers of the Orbitrap for the past few years before we passed the torch now to Lucia. Really sad, but you'll get to experience a lot of different breakdowns. So I'm really excited for you. And so I learned a lot during that experience, taking care of the instrument, really caring for it on a really deep analytical relationship. As Sergey mentioned, Anne-Marie was really the one that inspired me to do atmospheric chemistry. She gave me my first research experience as an undergrad, and that kind of shaped where I went in terms of graduate research. And then, of course, I want to thank Dawn for taking me on as a SART mentor last year. And I love this picture of us and Anne-Marie in front of the DC-8 before a flight that we were all on. This is a picture of me and Dawn on board the DC-8, I think during the flight before you fell asleep. But I did get a picture with you.
I wore the same outfit today.
Yeah, but that was a really great experience and something I'll never forget, getting really sick in the middle of the plane. However, I did not throw up. I was not one of those. So held it together. But Don and I worked a lot together, of course, during SARP, but also for the vaping project. And his lab was really instrumental in that. And so Simone is here, and thank you for all of your help with that project, and Barbara, of course, as well. I want to thank Professor Craig Murray for chatting with me all the time, just about life or science or things going around on campus, and getting a really interesting perspective. Want to thank the newly minted Dr. Zachary Cornwell for being a student friend and suffered together for many years. Now we're at the end. And I want to thank Professor Steve Bing. You always show up to all my events, and thank you so much. I taught for Steve, I don't know, like 6 or 7 quarters. It was a lot. And he was so patient with me. I didn't remember anything about circuits. And then in my first year of graduate school, I had to teach, junior students how to build circuits, and I didn't remember things. But Steve was so gracious and gave us a lot of tools in order to teach that in an effective way. So thank you so much for that. Then I want to thank everyone in the Discordo group, but most specifically when Avery and I joined the group in 2020, we had about, 3 weeks or so before the world shut down. And Doctors Natalie Smith, Alexander Clote, and Bahi Babumian really encouraged us and got us set up in the lab during a really hard time. And so we used all of their knowledge, even like till today, So that was really influential. Of course, newly minted Dr. Avery Dalton. Everybody knows that our relationship and how we went through this schooling together. So that's been really fun to do together. Lucia, my dear friend and benchmate, if you will, or deskmate. She's really an exciting researcher and has so much potential. She will pass her advancement. But keep practicing. Awesome. And so I want to thank also a couple of people, Michael Alvarado and Christina, who surprisingly made it today. I wasn't expecting to see you. For all their work. Christina helped me with the vaping project and was there really early when we had, yes, she did, when we had participants come in at like 6:30 in the morning. She came and helped me set up the instruments and get the experiments going. And then I want to thank Henry and Lauren for all their help with the iron work as well. I want to thank my funding sources. So NSF funded the iron research, NOAA funded the Urban Fires Project, and in the past year, I was awarded the Roland Graduate Fellowship, and so that supported me when I didn't have to teach in my last year of graduate school, which has been really nice. All right, and so for personal acknowledgements, like half of this room is full of my family. And so thank you so much for coming today. I know that there's a few people online from Pennsylvania, my Pennsylvania family, my California family is here. My parents, of course, my sister, Avery and Joshua, thank you so much for all of your support. Our dogs, of course, Gunner and Honey and Butter, who's passed away a few years ago, but he's our lab mascot. So he came to the lab, put him in my lab coat, my glasses, and it's on our group website, and that's really exciting. Of course, all of our kitties. So Kitty Purry is actually very famous at UCI. So if you take Chem 1X with Sergey, there's a question with an element called Kitty Purrium. And of course, Bob Marley and Freddie Mercury, our cats. And my grandma, who's not here, but I'm sure she's anxiously waiting for me to tell her that I'm a doctor. And I'll see her soon, but she's been so amazing during this process. She texts me every single day, have a good day in the lab, darling. And I text her back right away, and she's so excited for me and really great encouragement and support. And then lastly, I want to thank Sergey. We'll see if I can get through this. But Sergey is so supportive. This is a picture of him taking pictures of me at the last lead dinner when I won my awards. He was so proud of me. He was taking pictures from every angle, and there's a picture of us together. He came and met our cats once about a year ago. That was really fun. Bob was not afraid of you. He's normally afraid of everybody. So that was great. And then this is a picture of us. My favorite picture of us was in downtown Raleigh. We were walking around after an UCI event really late in Raleigh, and we found this, cat mural, this cat in heaven, and we just took a picture. We were so excited. You can see it in his face here. And this is a picture of us at Purdue, at a coffee shop there. That was a very special conference. So it was just me, Sergey, and Avery. We went to Indianapolis for the ACS conference there. And then we went to Purdue, and we spent a lot of quality time with Sergey and got to know him even more and learned some cool science. So I'm always forever grateful for your influence and support. All right, and with that, I'll take any questions you have.
Katie, kindly repeat the question from the audience to the Zoom people.
Oh, okay. Got it. Yeah.
So for your paralysis of building materials, the aerosols, talking about the photo enhancement versus photo bleaching. Thin PVC and thick PVC wire act really different. Why is that?
That's a really good point. And of course, I practiced that, but then. Oh, yes. So Steve Ming asked that for thin and thick PVC wire in my urban fire studies, they had different absorption properties. So for thin PVC wire, I had a photo bleaching effect, whereas for thick PVC wire, I had a photo enhancement effect. And so the difference between these materials, number one, we don't know where this thick PVC wire came from. It's like in the walls of the building, it's very old. And then for thin PVC wire, we did have a manufacturer for that. But this thin wire was purple in color, and then the thick was white. I wasn't able to identify any chromophores between the two, but they did behave differently. And I'm not sure, honestly, why. So it might just be that there was more PVC-like products there for the thick than there were for the thin. But to be honest, I don't really know. Yeah. Yes, Don.
So I have a question. Secondary organic aerosols.
Yes.
When I was your age, I don't remember that term. I mean, they were aerosols. They were just aerosols. And the whole, I'm just wondering sort of at what point did we have the technology and the intellect to start realizing that we had gas to particle conversion and they call them SOA. I mean, it's sort of a silly question, but
yeah, I guess thinking back to like the LA smog events, so 60s, 70s, 80s, around there. I don't know if that's was before my time, I think. When
my time.
when SOA became a terminology. But definitely when things started to become, more observable, I think, is when different classifications were made and different analytical apparatuses needed to be used in order to solve environmental and atmospheric questions. That's a good point. Yeah.
What do you think? So?
When people started building chambers actually in the 1970s, a lot of chambers popped up all around. So that's when they realized this.
70s.
I was wondering, you were talking about like how you were testing different temperatures, like burning at different temperatures. And I assume that's like kind of you're almost simulating biomass burning, right? In a way. These different temperatures, is there a certain reason why you picked 600 degrees or 400 degrees? Like, what's the temperature range that we're concerned with these types of events?
Sure. Yeah, so for pyrolysis, the range is between 300 and 800 degrees. So I just picked on each 100 mark to burn at. Of course, our furnace does oscillate in temperature a little bit. So it's give or take a few degrees that I was actually burning at. And so I wanted to see at each temperature what type of reaction could occur. Initially, we only started at doing 300 and 400 degrees, so kind of low temperature. Then nothing exciting happened, and then I got kind of frustrated, so I moved up to 600. And then it was clear when I started reading literature that actually it could oscillate between this range quite a bit. And so I wanted to do experiments at every single 100 mark there. But in a real fire, you're right, it could be a lot hotter than that. Obviously, flame combustion is order of magnitude higher or so. But in this case, if I were to have done flaming experiments in the lab, I would have produced mostly black carbon. And that really wouldn't have helped me too much if I was trying to understand like optical properties. Wouldn't have really been able to extract it. And if I could, it wasn't going to be able to run overtrap mass spec with it. And so in terms of brown carbon, we stuck with pyrolysis in that temperature regime. Yes.
I have a question from the Zoom.
Oh.
Curtis Malika from our group alum is asking, very interesting and applicable work nicely presented. Has there been consideration for pyrolysis experiments on household electronic items that could be viewed as potentially more toxic, e.g. EV batteries and funnels, televisions, computers, etc.?
Okay, so the question for Jim, I'm sorry, I didn't repeat the last one. The question was, have there been any considerations for burning electronics? Like commonly televisions, computers, commonly found in the home. Okay, got it. The answer to that is I didn't do it. However, oh yeah, he's on Zoom, so maybe I shouldn't have repeated. Sorry. But there's going to be follow-up studies coming from our group where Luis, my group member, he went to Colorado and did this campaign called the Basma campaign, and they burned a lot of materials. I forget how many. It's like 60. Yeah, so they did 3 different varieties of materials at different combustion conditions. So they didn't just do pyrolysis, they also did flaming combustion as well. And I don't know if they've done any type of computer electronics. Yeah, so structural materials, he says that they burned there. I wasn't involved in that campaign, but it's definitely an interesting component and probably should be done maybe in future work.
Oh, a lot of monitors. Storage.
We do, yes. and wires and things. So it's interesting, yeah. Yeah, please.
I was here with a photography data or graphic data. With the sort of technical, if you notice like the transition walk through on each would increase.
Yep. Yeah.
Was there a pattern in that? What types of walk?
Not really. So I only had two. Oh, yes, you're right. So the question was, in terms of chromatography, with my urban fires samples for photo enhancement or photo bleaching, do I experience in my chromatograms some peaks increasing in absorbance versus others that are decreasing at the same time to kind of like offset one another in effect? And so the answer to that is for two of the materials. So for the ones that were unaged or unchanged, so vinyl flooring and fabric that didn't have more than 10% change in either direction, I did see that. I saw certain peaks that went up after aging and then certain that went down. So we described that in the paper as more of like a complementary effect, and that in, gave a null absorbance change essentially with our bulk measurements, but no pattern that I observed so far.
Sounds like the questions are exhausted. Are there any more questions on Zoom? No, that's it for Zoom. Okay, well, let's thank Katie.